Yes, my name is Hans-Peter Schöner. In English, I go by Peter. That's much easier. Just to my background, I'm an electrical engineer with some mechatronics from the mechanical side and computer control. During my studies and my PhD, I have worked on the monitoring of batteries for electric vehicles. But then I started to work at Daimler, and I had been working at Daimler for almost 30 years. Last 15 years, I was responsible for testing methods for driving assistance systems, and the last 10 years also for autonomous vehicles. And I was responsible for the driving simulator as well. So a lot of things which are necessary to test highly complex autonomous or assistance systems which interact with drivers. So my plan here for today and tomorrow is to give you three big topics. One is the verification and validation of autonomous vehicles, seen from the automotive developer's view. That will be covered today. And tomorrow I have another time slot, and the first part I want to use to look at the Daimler's Bertha-Benz drive. I'll tell you tomorrow for the people who don't know that, in 2013. And then I will look more at the point of view of an authority who wants to release autonomous vehicles to the streets. And that's a question a little more different from the developer's point of view. But let us first start with verification and validation of autonomous vehicles. And again, let me start, where are we now? Maybe lots of you don't drive Mercedes high-end cars, but there are a lot of features which are available in the car. It's all kinds of assistance systems. I don't want to into detail, and they are just too many to explain even to the drivers. So they are sold as something like 1 star is good enough for Mercedes. Like, if you have this 1 star in your car, then you have a lot of things and you can trust in them. But they are things like assisting at night driving, emergency braking, braking on a point, braking even on cross-section, but following other cars and knowing about everything which is around the car. To see what is state-of-the-art, I show you this next short movie, which tells us what is available now. You can start a car from outside with an app. You still have to make sure you are there, and then you can drive normally. But the car knows where it is. What is the speed limit which is appropriate? Maybe when it's coming to a roundabout, to know there is a roundabout and you have to slow down to drive around a roundabout, even if you are in a mode of speed control. It knows about the curves. It can follow a track. It can pass other vehicles. But here, a situation where you didn't pay attention and this vehicle will still keep the distance and even slow down. And in traffic jam configurations, it is able to follow other vehicles, even when the markings are complicated with different colors, and even if the markings are not there. If there's a traffic accident among Mercedes cars, the information is exchanged so the other cars know there will be something ahead. And driving into cities, it will know now it's in a city. Braking, autonomous braking on cross traffic, on pedestrians which are not attentive. But if the driver acts, it will not do anything. And at the very end, of course, you can also park a car, being outside of the car, And all this is possible now already with vehicles you can buy, an S-Class, an E-Class, or cars of this size. And all those systems will probably be brought down to smaller cars like a C-Class or even an A-Class. And it's not only Mercedes-Benz, it's also other car manufacturers who are supplying similar systems right now. One of the important things of all those systems is the driver is still responsible for everything the vehicle does. It's assistance systems, and we call them level 2 systems. So if we talk about autonomous driving, I want to point out what is the challenge there from going from where we are now to autonomous driving. There are stages of autonomy which are defined by SAE, and level 0 is no automation. Level 1 is you have one specific function, but level 2 is what you have seen in the video. More than one control function, but driver is expected to be there. He is the one responsible of all the driving task, and he has to be available in short notice to take over and to turn off the system if necessary. But if we talk about autonomous driving, it's more level 3 and level 4 and 5. 3 means the vehicle takes control most of the time, and the real vehicle takes over the responsibility of being safe. And only the driver is expected to be available in certain complicated situations to take over, but not under short notice as here, but with comfortable transition times. And if you go to level 4 and 5, the driver needs not even to be in the car. Level 5 is the car comes without a driver and it can cope with all traffic situations. And level 4 is something in between. Yes, I'll come back to those again, but the big challenge is coming from here to here. The responsibility of safety goes from the driver to the vehicle. And that's the hard part. Why? Let's first look on what has happened now. We have introduced assistance systems to the cars, and those have to help the driver in situations where the driver makes a mistake. And up to now, on German highways, that's about 7.5 million kilometers between mistakes which lead to a big accidents. And in such situations, the assistance systems had to work. So that's relatively rare situations. Although most of these accidents, they are called, or if you watch in details at the statistics, you find out most of these accidents are due to human errors. So you think, okay, human errors we can help. But the challenging thing is, in between, there are 7.5 million kilometers where the human driver doesn't make those mistakes. He does a lot correct. And now we want to automate all those things. And that means we have to drive those 7.5 million kilometers and maybe even more without any mistake, without any dangerous mistakes, of course. Look at the numbers. There is a category of severity level. S0 is a crash which only has material damage, but not personal damage. S1 is minor, S2 is severe personal damage, and S3 is humans die. And you see that's about those 600 million kilometers between accidents where people die, and that's 0.15 times 10 to the minus 8 per kilometer. Or if you say it's with about 100 kilometers per hour, it's something like 10 to the minus 7 per hour. That's the occurrence rate of deathly accidents in the actual statistics of German highways. And it's very similar. In Sweden, it's a little less. You have longer distances and less traffic. In the US, it's significantly higher, and in most parts of the world, it's significantly higher, a factor of 10 to 100 higher than those numbers. So these are pretty good numbers, and everybody accepts them, that this 10 to the minus 7 per hour is an accident rate which is acceptable. What does it mean for level 2 and 3? Level 2, again, the driver watches. Level 3, the driver is allowed to leave the steering wheel and to watch other things like smartphone, whatever, reading emails, writing emails, and so on. In level 2, the system is designed so the vehicle, the driver can respond with a reaction time of 0.7 to 2 seconds, which is this normal range of reaction times, to warning tones, which tell the driver, now you have to react something. In level 3, we talk about reaction times of 10 seconds, which will probably be in the law. But even if you have lower reaction times, from 2.5, about 5 seconds, 5 seconds is, from my experience at the driving simulation, the time period when most people, 95%, can react on some warning or something like that. But a lot more, the other 5% need between 5 and 10 seconds. What does that mean? If you're driving at 100 kilometers per hour, that's about 30 meters per second, you drive in those times 75, 150, or even 300 meters. 300 meters, if you look out from your car, 300 meters is something you barely can see what is there. So if you talk about 10 seconds reaction time, everything has happened in traffic. It's more like 3 seconds ahead, you see what is going to happen, maybe 4 seconds, but not much more. And if you think of you want to stop at a decent deceleration between 4.5 and maybe 10 meters per second, which is the physical limit at a dry road, then you come down to something like stopping is another 45 to 100 meters. And if you add those up, the reaction time of 2.5 to 10 seconds means 120 to 400 meters. You have to know in advance whether the driver has to take over or not. That means emergency handling has to function without the driver. You cannot afford to tell the driver, oh, I have a problem now, I cannot brake, do something. The vehicle itself has to do it. It has to solve every urgent problem on the road by itself. If not, it doesn't work. So this is my summary. Before an autonomous vehicle will drive you anywhere, it has to prove that it will not drive you into trouble. So how to prove that? And first we have to look at what is really the risk. Look at it from an engineering point of view of not only I'm afraid, but what is really the risk. Look at other fields of controlled risk, aerospace, electrical power systems, power plants, nuclear power plants even, but also production automation. They all use one standard, IEC 61508, which is the basic for how to deal with risks. There's one specific automotive version of this 61508. It's called the ISO 26262. And that's a risk-based safety standard. It looks at hazardous situations. They are qualitatively assessed, and each situation should be avoided, each dangerous, risky situation should be avoided by systematic control design or avoidance procedures. And also random hardware defects have to be avoided in a way that the number of faults per hour is less than those 10 to the minus 7. There's much more to it. If I would go through that, that's a whole lecture on its own. But the basic is we talk about hazardous events. They have to be identified, what might happen, and what would be the consequences. You have to set up a safety goal, which is a quantitative goal, what kind of level of safety you want to reach in numbers of failures or deathly accidents per hour. This leads to safety integrity levels. Depending on what kind of system you automate, if it's a really dangerous system like autonomous driving, you come to an ASIL D level, which means very rare accidents, and that comes to the level 10 to the minus 7 per hour. And this is used industry-wide. And from that, it's broken down to all the components in the vehicle. What is the safety requirement, the reliability requirement, and the availability requirements for that single component. As before I said, this safety level assessment looks at 3 things on the level of risk. One is the severity of an accident, the exposure. That means how often do we come into a situation where that could happen, from incredibly unlikely to high probability that would happen almost on every drive. And then controllability classifications. That means in case you come into that situation, will you or your vehicle be able to control that situation? If it's, the car in front of you is just braking, okay, that happens all the time, but it's easy control. You have a control, you only have to watch. You have a brake, and then it's in general controllable. But if suddenly on the highway, in German we call it a ghost driver, somebody coming ahead from you on the wrong lane, it happens so fast, it's most of the time it's not controllable or very difficult to control. So those are necessary to calculate the risk, and normally the risk is a multiplication of the 2 factors, the severity, the 1 minus controllability. So if the controllability is 100%, this goes to 0, the risk is 0. And E is the exposure, how often do you come into the situations. And of course you have to sum this up over all relevant risky situations you can think of, and even those you cannot think of. And again, the ASIL concept then, with these severity classes and probability classes and controllability classes, says, okay, you need some kind of ASIL class. This is standard for all components in cars, and ASIL D is, if you want to drive autonomous, it always ends up in ASIL D, the most relevant factor. So how do you design a trustworthy system? We have seen several examples, and I think you have touched that idea yesterday already. First of all, redundant self-monitoring concepts. Redundant means in a system design you have some critical systems with high failure rates. You need several of them. And then if one fails, the others can take over. And then you can calculate the failure rate of the complete system. Important is that these formulas for the mathematical treatment only works if all subsystems are uncorrelated. If all those systems are supplied with the same power source, and this power source fails, then all of them fail at the same time. So then you don't have an improvement in reliability. So you need to make sure they are uncorrelated. And you do that by using diverse components. You don't take 3 camera sensors. You take a camera, you take a radar, and you take a LiDAR sensor, for example, in order to have diverse components which fail under different conditions. Besides that, you do a fault tree analysis. You look at your system, what is the logical structure, and you ask, if one system fails, what is the result for the total system? You try to avoid systematic errors like supplying all of them with the same power supply or something like that. And okay, if you have done your work correctly, you can use a mathematical model to calculate the failure rate, and that's required in the 26262 ISO standard. For testing, now it's different than testing just, does it work or not? You have to evaluate your system integrity indicators. So that's this blue part, which looks at the system and which shows, is there a component which failed? And if there's one which has failed, you cannot wait until the next fails. You have to do something. And your system integrity monitor is the one which takes the responsibility for the whole system to monitor, is everything okay? Can I still continue working like that? Then you have based your mathematics on component failure rates. You have to verify that during testing to find out whether under these configurations it's still valid. You have used those failure rates from previous experience, and that could be something different in your application. And you have to verify that there is no correlation. Quite often you do that during the testing phase. You find whether single components fail at the same time, and you ask why. That's important. And verify rejection or fault propagation. If really one component fails, you have to test whether your system really behaves as you designed it. You want that it can continue its work even though this single component failed, like we have seen with the quadricopters this morning. That's one way of dealing with that on a component level. All this is a standard since 2011. It has been used for the development of automotive systems up to now, worldwide, at least at all the large car manufacturers. But you find out that with this ISO 26262, there's still something missing. The ISO 26262 defines some kind of risks on the highest level. The question is, did you cover all the risky situations? Did you think of all? And it's not really covered in a standard how you do this. There's a new one which was just released this year, and it's not final. It's in development phase, and it's the ISO 21448. It's called the safety of the intended functionality. And it tells you how you should proceed on how to find out if you covered everything. And it covers a lot. It does not cover that somebody intentionally tweaks the system to make so these are the security aspects. This is not covered there. But all the other from technical part, it's covered. And it's giving you some guidelines on how to design such things. Internationally, there are two requirements for autonomous vehicles now which have been written down. And one in the EU system, there's this sentence, when in the automated driving mode, the vehicle shall not cause any traffic accidents that are rationally foreseeable and preventable. So foreseeable and preventable. If you don't foresee it, you might miss something. And preventable, you might foresee something and there is no way of getting around this accident. It is accepted according to this sentence. The United Nations have a slightly different wording. Automated vehicles shall not cause any non-tolerable risk, meaning that under their operational domain, it's important, under the conditions for which they are built for, they shall not cause any traffic accidents resulting in injury or death, that's the same, that are reasonable, foreseeable, and preventable. So that's the same condition again.
Who is the second one? Which organization is that?
That's a United Nations working group, WP, yeah. If you look at that more in a picture, driving with a vehicle in the world, an autonomous vehicle, first you need, what is my operation design domain? Do I really want this vehicle to run under all weather conditions? No. No human driver would drive out in a snowstorm. Why should I require to do that with an autonomous vehicle? So I draw a limit line and I say, this autonomous vehicle is designed for good weather conditions and it's designed for normal traffic and maybe only on highways for a start. So we cut away a lot of very risky parts, but then we require that the vehicle by itself can decide whether it is within the operational driving domain. That's part of the responsibility that the vehicle has to decide I'm in or out. It has to know the weather forecast. It has to know what type of road it's on. It has to look at the conditions of the traffic. Within the operational driving domain, yeah, we have the reasonably foreseeable. So there are some normal traffic situations which might be dangerous, but all the preventable, which are physically preventable, we have to improve the performance that we don't have any risks from that. Unpreventable, come back to that a little later, might be somebody is throwing stones from a bridge onto the highway. If you're coming there in that moment, you have no chance. That's an unpreventable accident. But you still have to look at, to reduce the risk for such a situation. What can you do? You have to think of that. But it's not the requirement that you have to come out without an accident in those situations, but to reduce the risks. And then here's a very important part. This is what everybody knows. But there is a big part what people just don't know when they design a system. A lot of those things come as experience when you bring it into the market. When you start using it, you find out things. Oh, there are some unusual situations nobody has thought of, not even the best expert. And you have to find out how to work with that. Foreseeable and unforeseeable. Unforeseeable, that was this one. And unreasonably foreseeable, those are the situations where some professors from the US, they brought up a question some time ago. If an autonomous vehicle drives along the road and there is a young lady with a baby on one side and an old person on the other side, and it has to decide to run down this person or that person, what is the ethical result on doing that? Actually, I think, and many people in the world think, that's foreseeable. You can imagine that something like that happens, but it's unreasonably. There is no single situation in all the statistics of the world that an accident like that has happened. So, and no human driver would even distinguish whether it's an old person or a young person. If it's on my way, okay, I try to brake, and if I hit it, that's it. But if I leave my way and drive through the path where normally you should not drive, and you hit somebody there, you better don't do that. So there are some results on your behavior of the system, what you should not do to avoid such systems, but you cannot claim that here you will come out without any accident. Okay. And again, this may be the same information: foreseeable, unforeseeable, preventable, unpreventable. Foreseeable and preventable, here you can think of situations, of scenarios which you can test. Unforeseeable and preventable, you have to learn what are new things and to find a way to work with that. And you have to implement a learning procedure. But then there are those foreseeable, unpreventable things. Yeah, here you only can avoid some huge accidents, but your mitigation, reducing the risk is the main goal. And there are still things, they are unforeseeable and they are unpreventable. And even a human driver cannot do anything with that. The bridge which collapses just in front of you, like in Italy some time ago, it's not the driver's fault. It could not be the fault of an autonomous vehicle, but there is still some risk of some accident, and we need insurances for covering that. That's normal even with human drivers. Now let's look at this risk equation again and look back. As the severity, it has been addressed by all the passive safety systems in cars. Limit the consequences if you come into an accident, provide suitable protection, and facilitate rescue. Master extreme situations, that's the field of controllability. That's the driver assistance systems domain. Detect dangers early and react fast and appropriately, and up to now help the driver to do that. All this we need for autonomous vehicles as well. But the exposure, how often do you come into critical situations, up to now has been reserved for the driver. He was responsible to find ways or to drive in a way that he doesn't come so often into dangerous situations. And that's a new task for autonomous vehicles. And what is that? It's looking ahead. It's driving predictively. So that is look ahead, know early enough what you are going to do. But this means also drive in a way that others know what you are doing. Put your turn indicator. Don't brake too hard. Things like this. But also know your own limits. Don't be surprised by some traffic situation which you cannot handle. Drive in a way that you can handle those situations. That's a new option with autonomous driving. What does that mean? All the traffic situations you can divide into, most of them easy, normal driving, but then there might be complex situations. From them, the critical situations may evolve, and those lead to accidents and severe accidents. And I put this into these two coordinates because we can choose independent parameters and controllable factors. Bad weather, chaotic traffic, missing infrastructure would make it more difficult or more complex to drive. But there are always ways you can reduce the risk and reduce the exposure to risky situations by reducing your speed, increasing your distance to other vehicles, and by increasing, or by good lane keeping, which is the lateral distance to other objects or other parts of the traffic environment. So what you have to do is, if the situation gets worse, do something to make your driving more simple. One of the key things people have to learn during driving school. Okay, I go through that. What kind of reasons for accidents do we have? First, we have failure of components. Hardware deficiencies, something doesn't work, like the one rotor in the quadrocopter which fails. Actually, in traffic accidents, we have only 1% to 2% of actual statistics of accidents. The components are designed very well, and they are not the main cause for accidents in modern vehicles, at least for new ones. If they age and age after 10 years, you get more and more like those problems. They are designed according to the ISO standard. And there are well-established testing procedures on benches, on mechanical testing devices, and on test fields. So I think this is well covered. And that will not be different for autonomous vehicle. It will be the same thing, only for more components. What is more challenging with autonomous vehicles is deficiencies in sensing road, traffic, and environmental conditions. A camera would have a picture like that. Actually, I took this picture in Sweden some time ago. Low-level sun, rain just finished, and you had a strange traffic situation. You barely can see, okay, here are merging two lanes. So you have to watch for oncoming traffic. Is this oncoming traffic or not? Yes. So situations like that, you have to test in real worlds. It's almost no way to test them on the proving ground alone. You have to drive around the world, because if not, you don't see all those different situations. But of course, you can test the behavior of the vehicle in such situations when you are on the proving ground. You can test the behavior of a failure of a sensor and then find out on the proving ground what the vehicle will do, but also driving in real traffic, getting experience. It's needed. You cannot do without that. A third reason for accidents is deficiencies in control. The control algorithms. That's something like the situations, your sensors, your whole software tells you, oh, something is strange, like this. A human driver never has seen a situation like that during his driving lessons, but he has an idea what is that. But you have to define something for an autonomous vehicle to think of a situation like that. Google is talking about a bunch of ducks being chased by a lady with a wheelchair or whatever. That's a symbol, the same situations. And that's, again, a picture I have taken. And there are so many strange situations nobody would think of. But even the ones you would think of, you can test. There are a lot of complex situations with a lot of variables, with a large parameter space, but they may be decoupled from the physical sensor input, and so they have a high potential for testing of simulation. And so using simulation tools, these control algorithms are easy, not easy. They are tasks which can be done in the office, in the laboratory. You don't have to drive out on the street to do that. Another thing is behavior dependence. Know and obey the rules. Even for human drivers, it's very hard to act adequately to the conditions. Driving with too much speed, driving, inattentive, sleepy, distracted. But first of all, you have to know what are the rules which are valid at this point where you are. What do you have to look for? And the second is, are you capable of doing that? Driving drunk is some example where it's quite easy to be better with an autonomous vehicle. But driving drunk for an autonomous vehicle, the autonomous vehicle has to judge whether all the sensors are okay, whether all the computing systems are okay. All the systems have to be functional. If they would start without that, that's something like driving drunk for a human driver. Okay, and again, something like that you shouldn't do, and that's the important thing. If you think it's getting more complicated, do something. And there's one fifth category of accidents, and that's the faulty interaction of the driver and the vehicle. Does the vehicle understand what the driver is telling to the vehicle? And does the driver understand what the vehicle is telling to the driver? For early aircraft automation, this was the major cause of accidents. The pilot brought the vehicle in an autonomous flight mode, but then something happened and he hit the control stick. And in early times, this was the signal for the automation system of the aircraft. Oh, the pilot wants to take it back. So give it back to the pilot. And it was a small light which turned off. Now it's again in pilot mode. But the pilot just continued flying, and the aircraft is stable when you don't touch anything normally. But if there is no pilot who controls that, it can give severe accidents. So it's very important that the human-machine interface works well, so the driver or the pilot understands now it's in the responsibility of the vehicle, and the other way around the same. And to check that, we have driving simulators where we can test the interaction of real humans with at least the software which is within the vehicle, and do experiments to understand well what is really happening. So in summary, we have those hardware components, those 5 categories, and there are 3 which are related to external conditions. It is mainly you have to understand what exists in the real world, what kind of situations there will be, and what kind of weather conditions are there. So that's a matter of standardization on what do you want to test, what do you have to test. And here, the components and the human-machine interface, it's very design-specific. So that was the reason on those things we talked about with other companies, with other automotive vehicles, and that's who has the best design mechanically and or electronically, and also from HMI. And to test those different things, software in the loop is the things which you can do with those 2 categories. And driving simulation is the one, and that was one of my tasks, to work on those simulation tasks. What kind of tools do you need for that? This is well established, and this is field test, mainly field test. Let's have a closer look at the controllability and what do we do in the driving simulator. That's we call it dome. It's at the interior wall you can project a virtual world, and there's a whole vehicle in there. And with this projection of the virtual world, you give the driver a setting so he's driving in this virtual world. And with this actuation system here, you make this simulator move, so the person in the vehicle has also the feeling of driving in a vehicle, acceleration, decelerations, curve driving when you are pressed to the side. This is done by the actuation system. And of course, very important is a sound system in there to tell the person what's going on with the other channel. And you control that from a control room. Just some examples. That was emergency braking development on testing on a pedestrian, which comes out here. You design that in simulation. You can set up how a pedestrian jumps over here, and you have something going on there to take to attract the person who is driving to watch that, and then it's a bigger surprise, and you get a wider spread of reaction times of the persons. And with situations like that, we found out in such situations it's too late to brake. And that's the other situation. You come here and there's a car coming from the right, and he might not have priority, but he cuts in. And here in this situation, yes, in that situation, you cannot react as a driver. You cannot react fast enough. And that was the reason that we designed systems to be able to perform in those situations autonomously and not waiting for some driver response. So that was the first step of autonomy. But the good thing about the simulation here is you can do things like that, which are an accident, but which are really not dangerous for the driver, for the test driver, for the persons with which we tested those situations. Looking at the driving simulation situations, you can summarize the result with this kind of graphics. Here is the portion of drivers who can avoid an accident, and here is the main parameter which controls this behavior. So if your object, like the crossing car or the crossing pedestrian, comes out very early, you have enough time, then about 100% of the drivers can avoid the accidents. But there are also unavoidable accidents, as I said before, the stone drop from above. If it's too short, you cannot react. And there's this curve of the normal driving population with distraction. If you have a warning system, an assistance system in the car, which warns you when it sees something like that, it will be a lot faster, or at least a lot of the people which are not attentive, they will react much faster. So the green line will be the performance of the population with an assistance system. But still you have unavoidable accidents. They're a little shifted more to the left because there is the reaction time of the driver is significantly reduced in average. So you have accident avoidance until a certain time to collision. And below that, at least in average, you have accident mitigation. But still the unavoidable accidents. If you would brake autonomously with an autonomous vehicle, you could save a little bit. And that's the reaction time. Normally, you warn somebody and the driver has to react. That takes some half a second or something like that. And a radar is a little faster in detecting speed differences to the vehicle in front of you. So that's the reason why it's here, but still there are unavoidable accidents. So that's the matter of controllability. The main message is, with all kinds of situations where you are not controlling the complete situation, you cannot make sure that you control 100% of the situations. So this part here is the dangerous part, and you have to avoid that by reducing the factor of E, the exposure. So how can we reduce the exposure? let's look at what we can see. Here, you guess what this guy is doing. This one is just walking, but this one is starting. He jumps across the street because he wants to get out of the rain. And so you know he's running fast, but just from before he even is on the road. What about this guy? He will pass along the car. You see that from here, even though he was still on a straight trajectory. And so that's looking ahead, and nobody has done testing procedures up to now. We have been implementing them at Daimler, and we're working on something like that, define adequate test cases, which should be done by everybody in order to be able to do something like that. So now, by now they have better tools of simulating that. And then let's look at the driver again. I will come back to that tomorrow a little more. Very important is no driving pupil is tested for collision avoidance. He is tested for situation assessment. He's for judging his own skills, for judging the conditions of the vehicle, own position and rules and their limitations. And he is tested whether he can update his plan in due time, that he can handle surprises. He has correct assessment of his own and of other people's reaction times, and he has to be able to handle cooperative driving situations. This needs to be tested as well. And a lot of this, for human drivers, they learn over the time. So the same challenge as with autonomous vehicles. And yeah, we need to define measures for safety of driving in order to work quantitatively with that. Okay, so that's this. The vehicle has to judge whether a situation is still acceptable or if it's getting dangerous in order to do something. This is the basis for learning behavior, and in addition, it has to show that it can reduce the level of danger by its own actions. Yes, I said that a little before, but I want to point it out to stress this. The vehicle offers, an autonomous vehicle offers an autonomous mode. It is not set in an autonomous mode. You cannot force a vehicle to take over the responsibility, only if it really accepts it. And so normally that's the idea of most car manufacturers. The vehicle will offer this. You dial in where you want to go, and the vehicle gives in a response. I can give you maybe 80% of this drive you can drive autonomously. Or maybe you can take the shorter way, and you have only 30% of autonomous driving, or you can take the longer way, and on the highway I can give you 80%, 90% of autonomous driving. The rest is your task. And the vehicle shall be able to handle any reasonable, expectable situation without driver interaction. And it will give back the task of driving to the driver in a long enough time, around 10 seconds, to tell them, now it's your task again. And that means when they come out of situations where the operational design of the vehicle is not able to fulfill those tasks. Okay, I have some more slides on simulation. I have to go a little fast on that. The traditional way of testing vehicles is looking at a black box, driving for a certain distance, and evaluate what kind of critical situations came out. If you want to do this for autonomous vehicles, you would have to drive for hundreds of millions of billions kilometers to test it with a statistical relevance that you can say it's that safe as you want. And it's not sure to do that. Driving around in the world will drive somewhere in the space and you might miss critical situations. So that's not even a good way. So the new situation is make a white box testable design, separate your function into subfunctions, simulate and test your subfunctions separately with artificially introduced test cases and result verification. And then define your operational limit under which you can prove that it works and do the tests on the proving ground to verify that you are safe within this operational domain. Yeah, go through that a little fast. Testing, field test, we need that to find all those unknowns. On the proving ground, we can test some specific case, but not all of them because it would take too long. Most of them has to be done in virtual tests. And for this kind of process, there has been a research project within Germany which just finished, which developed the procedure. And yeah, one of the key points is using simulation with a virtual driving simulation platform. What you need for that is road models, traffic models, what is the behavior of the other vehicles especially, but also what is the model of your sensor, how does your vehicle perceive the virtual world in the simulation to replicate the real behavior in the real world. And then of course you need vehicle behavior, and then you can plug in your autonomous drive control software to verify what's going on. And let me skip to some. Yeah, I think I need to do that. So what are the kind of situations we want to test? Challenging traffic situations looks like very easy. Following on the highway. But following on the highway gets challenging when the vehicle in front of you brakes behind a standing end of a traffic jam. The worst case is not when it's making a full brake, but the worst case is when this vehicle crashes into this end when the driver was not attentive. Of course, you can talk about if I have a convoy, a platoon, I can communicate between those, but for the next years, you cannot make sure that this vehicle has a communication. So if you just follow this, you have to assume this will crash into the end of that. And that's a challenging situation. Nobody really can cover quite well for high speed. Cut in seems to be normal, but cut in when this vehicle comes to the end, it has to cut in. And maybe here is a very tricky situation. That is one of the challenging parts. And cut out seems to be even more easy, but cut out because there's something on the road or even an oncoming vehicle, you have to find some solutions to that. Okay, I skip over that. And finally, on the proving ground, what you do is you have certain situations which you simulate. You find out that's a critical case. On the proving ground, you have to replicate the same case and to find out that the vehicle is really behaving in the same situation, the same way, and then compare the simulation and the proving ground maneuver to make sure that this works together. And, sorry, this is a short final video now on on the simulation tools at the driving simulation center at Mercedes, looking first at environmental models of the car, setting up the road network, doing some virtualization of the real world, abstracting it to the important things, looking at traffic situations, like here a priority thing which you can simulate, but also looking at your sensor models so they really can replicate the real world. Then you have to think about the scenarios. Of course, difficult situations are the challenging part, complex situations. It's a lot of work to design those, but those can be the same for a lot of car manufacturers. So this is a field of cooperation, but testing it with your own driving software is a challenging part to do all this with human drivers, but also testing the software with a lot of different traffic situations which you need to configure traffic density, to configure situations. Cutting situations are especially difficult. And the test automation is looking at all those different situations with a lot of different parameters on what would happen in the worst case, and to find out where is your limit of what you can do and what you cannot do. And all this together gives you the testing environment to do testing in simulation. And yes, just to summarize, what is essentially new for testing of autonomous vehicles? There will be much more simulation, especially for verification of control algorithms and rule compliance. The systematic search for rare functional deficits, that's a challenge. And up to now it was driving kilometers and kilometers, but you have to finish before you really can come to an end. So you have to invent those critical situations. A lot of this you can do by combining single partial events which don't cause an accident, but the combination of different things, that are the reasons for rare events. And then the functions, you have to assess whether you still can cope with those conditions if you understand the rules. You have to judge as an autonomous vehicle whether the limits of autonomy are getting close, to wake up the driver and to announce this early enough so the driver will take over. And the worst case, if the driver doesn't take over in level 3, then you have to come to a safe stop. And a safe stop would even be stopping on the road in the center of the lane if you have no other option, and waiting the 10 seconds until the driver takes over. And if it doesn't take over after 10 seconds, you might have the same problem as a human driver with a heart attack on the road. So there must be a bigger problem. Okay, in summary, it takes a lot more simulation to test the functional requirements, but that's only one part of a very big field of getting the autonomous vehicle to run. And more on that tomorrow. Thank you.
Brilliant. Thank you very much. And you will be here for a couple of days.
I will be here tomorrow, and I will be here on Thursday. Yes, so I'll be glad also to continue discussion with a coffee, but you decide what is now. I'm a little late now.